Okay, guys. In this today's class, let us study about how to solve or how to handle different types of loads in our analysis of beams. Okay, now let us look at this problem. So you have a beam which is fixed at other ends. You have a point load. So you can see here you have a point load over here, okay, which is acting exactly at the center. 10 kilonewton is a point load, and you can see a moment which is 20 kilonewton meter. Okay, now what we are going to find out, in this problem is, for the beam shown in figure, determine the displacements by taking E is equals to 210 GPa and B is 0.2 meter and H is 0.4 meter. So he has given us the dimensions and the Young's modulus. So what you are going to do is 210 GPa. Since if you look at this, you ensure that you resolve all the beam problems in terms of meters. Keep all the dimensions in terms of meters when you are solving the problems on beams. So E is equals to 2 into 10 into 10 to the power 9 Newton per meter square. Giga is 10 power 9. So Pascal means Newton per meter square. So B is 0.2 meter and H is 0.4 meter, which will be, I'm going to keep it as it is. Now, so this is the actual problem. Now we need to build a finite element model. So how are we going to build a finite element model? So as usual, drop the lines from the ends. Okay, drop the lines from the ends, place the nodes at the ends and join them with a straight line. Okay, now have a look at it. The point load from the point where exactly, from the location where the point load is acting, just drop a vertical line. Where exactly it is going to coincide with the horizontal line, place a node. Meanwhile, the point where exactly, about which point your moment is acting, from that point also, if you try to drop a line, both are intersecting at the same point. So this node is sufficient of taking both the boundary conditions. Okay, so now give your node numbering from here, extreme left. Node number 1, node number 2, node number 3. Club two nodes and form an element, element 1 and element 2. Okay, now I'm going to write the degrees of freedom. If it is going to move in this direction, it is v1. If it is going to move in this direction, it is theta 1, angular displacement. At node 2, v2, and angular displacement is theta 2. And at node 3, it is v3 and theta 3. So that is how we're going to solve the problem. Now, first and foremost, our intention is to find out the stiffness matrix. For the stiffness matrix, what all we need? EI by LEQ. Moreover, what is this? E is Young's modulus, I is a moment of inertia. That is area moment of inertia, and LE is the length of your element. Okay, so you can see that length of the element 1 and length of the element 2 is both same. That is how much? 3 meters and 3 meters, which I have written here. Length of the element 1 and length of the element 2 is 3. And since both the elements are having the same dimensions, so I1 is equals to I2 is equals to BH cube by 12. So it is a rectangular cross section. So B is 0.2, H is 0.4 cube 12, 0.4 cube by 12. Okay, if you do the simplification for this, you are going to get 1.067 into 10 to the power minus 4 meter to the power 4. Okay, now since LE1 and LE2, length of the element 1 and length of the element 2 is same, I'm going to do the multiplication, because I need 6 times of LE, 4 times of LE square and 2 times of LE square. Okay, in my stiffness matrix. So 6 times of LE, that is 6 into 3. LE is 3. 6 into 3 is 18. Okay, LE square, that is 3 square is 9. 9 4s are 36. Again, LE square, that is LE is 3. 3 square multiplied with 2. 3 square is 9. 9 2s are 18. Okay, now I have all the values with me. So what do I need to do is E, because I have determined I, okay, and I have determined 6 LE, 4 LE, 4 LE square and 2 LE square. Now let me determine EI by LEQ. So since for element 1 it is E1 I1 LE1 cube, for element 2 E2 I2 LE cube 2. So E1 and E2 is same. So 10 into 10 power 9, and I1 and I2 is also the same. So 1.067 into 10 power minus 3. So length is 3 cube. So if you do the simplification, you are going to get 8.3 into 10 to the power 6. Okay. Once you have got that, I'm going to substitute in the equation. Okay. See, if you look into it, so 12. So 6 times of LE is 18 minus 12, 18. So if you do the, see, 12, 18 minus 12, 18. So that has been written. So I have written both the stiffness matrix. Okay, for element 1 and element 2. Now what we need to do is, okay, look at the diagram. Now in the stiffness matrix, I need to write the degrees of freedom, because that is very much essential for us to form a global stiffness matrix. So I'm going to write that for element 1, V1 theta 1, V2, theta 2 are the degrees of freedom. So I'm going to write it V1, theta 1, V2, theta 2 are the degrees of freedom. So similarly, for your element 2, so this is element 2 which consists of nodes 2 and 3. So V2, theta 2, V3, theta 3 are the degrees of freedom. So V2, theta 2, V3, theta 3, V2, theta 2, V3, theta 3 are the degrees of freedom. Now, so how many degrees of freedom does the problem has? 1, 2, 3, 4, 5, 6. So the stiffness matrix order will be 6 cross 6. Okay, how are we going to form that? So first you write all the degrees of freedom in a sequence. V1, theta 1, V2, theta 2, V3, theta 3. V1, theta 1, V2, theta 2, V3, theta 3. With the help of a element stiffness matrix of element 1 and element 2, I'm going to form a global stiffness matrix, which we already know. So follow the same procedure for forming the global stiffness matrix. Now, next one is global force vector. So here, global force vector, again, it depends on the displacements. See, at a node, you will be having a linear displacement and the angular displacement. Okay, so for the linear displacement, force, transverse force is responsible. For the angular displacement, moments is responsible. So F and M. So F1, M1, because 1 is going to represent node 1. So 2, node number 2, 3, node number 3. So if you look at this problem carefully, look at the actual problem. So node 1, at node 1 you can see the diagram, it is completely fixed. Node 1 and node 3 are completely fixed. So which means that there will be no transverse deflection, okay, and no angular deflection, okay. And sorry for this, not the deflection. Is there any force acting at node 1? Is there any force acting at node 3? No. So literally for that I'm going to take 0, 0, 0, 0. Okay, there is no force and there is no moment acting, so that is why I'm going to take 0 and 0. Now look at this. At node 2 you have a force that is how much? 20 kilonewton, which is acting, but it is moving in the opposite direction, or it is moving in the negative y direction. So what I'll do is I'll take a sign convention as minus 10 into 10 power 3 Newton, and M2 is also 20 into 10 power 3 Newton. You may ask, have I taken it positive? Yes, I have taken positive value. Whenever the moments are in counterclockwise direction, you are it is positive. That is a sign convention. Okay, sign convention. What is a sign convention? Means whenever a moment is okay, see, in the problem given at node 2, you have a point load and you have a bending moment. The bending moment is acting in a counterclockwise direction, so sign convention is positive. If the bending moment is going to act in the clockwise direction, you are going to take it as negative. Okay, wow. So I have written node 2, F2 is minus 10 into 10 power 3 and moment is 20 into 10 power 3. Okay, then again coming to the diagram, look at the diagram carefully. See, node 1 and node 3 are completely fixed. So in order to apply the boundary conditions, what I'll do is I'll take V1 theta 1, V3 theta 3 as 0, because they're completely constrained at the ends. So on that behalf, V1 theta 1, V3 theta 3 has taken as 0. Once you take that as 0, so what you need to do is in the global equilibrium equation, you need to delete the respective rows and columns which are associated with V1 theta 1, V3 and theta 3. See, I have deleted the V1 theta 1 columns as well as V1 theta 1 rows. Similarly V3 theta 3, I have done the same for V3 theta 3 also. So once you delete all the rows and columns, ultimately you will be left out with only 240072. So if I have written that 240072, and the common is 8.3 to 10 power 6, and on your RHS you have minus 10 into 10 power 3 and you have 20 into 10 power 3. Okay, if you just solve the above equation, you are going to end up with the unknowns, that is V2 50.22 into 10 power minus 6 meters and theta 2 is 33.48 into 10 power minus 6 radians. Okay, this is the solution what we require. Okay, meanwhile I have solved one more problem also. Let us solve one more problem. So here you can see it's a cantilever beam which is subjected to UDL, uniformly distributed load, whose magnitude is 10 kilonewton per meter, and a point load at the free end which is 100 kilonewton, and the Young's modulus is Young's modulus E is equals to 70 into 10 to the power 9 Newton per meter squared, and moment of inertia is 4 into 10 power minus 4 meter to the power 4. He has directly given the value of I. Okay, now I'm going to form the finite element model. First, what I'm going to do is I'm going to drop the lines from the ends. Okay, from both the ends I've dropped the lines, vertical lines, and I'm going to place a nodes, and I'm going to join the nodes with a straight line. Now, if you look at the problem, see the UDL is acting on the entire beam, okay, and the point load is acting at the end. So there is no new node is essential to represent the loads. Okay, this UDL which is acting on the entire element, okay, so one element is sufficient, and whatever the point load which is acting, that will be acting on the node. So one element is sufficient, or in other words, give the node numbering from your left, that is node number 1 and node number 2, and combine two nodes and form an element. Okay, so I'm going to write the degrees of freedom. Node number 1 v1 theta 1, node number 2 v2 theta 2. So generally this is how we are going to write it. Now as usual, E is known, I is known, L, length of the element is 4 meters. So let me first directly go with finding out the stiffness matrix. We know that stiffness matrix is given by EI by L cube 12 6LE minus 12 6LE 4LE square minus 6LE 2LE square. Okay, 12 minus 6LE and 4LE square. Okay, E is given, that is 17 into 10 power 9. I is also given, that is 4 into 10 power minus 4, which is being given. So here also our intention is to find out the displacements. Okay, just like this problem. So he is asking us to find out the displacements. Okay, so our aim is to find out displacements. Now, so if you do the simplification, okay, CL is 4 cube. So if you do the simplification, you're going to get 0.4375 into 10 power 6. Meanwhile, I want to find out in the stiffness matrix, I want to find out, I need the values of 6LE, 2LE square and 4LE square. Okay, I'm going to find it separately. So since LE is 4, 6 4s are 24, and 4 times of LE, 4 4s are 16, 16 4s are 64, and this value of 2 LE square is 32. Okay, so this is how we are going to find out. And one thing here is, since it's only one element, okay, yeah, I'm gonna have I have written the stiffness matrix for that element over here. Okay, just have a look into it. I've written all the values. Sorry, this is no, this is not the stiffness matrix. Yeah, here I have written the values. Okay. Let me write it once again. So 0.4375 into 10 to the power 6. So 12, 6 times of LE is 24, minus 12 as it is, what do you have, 6 LE, so which is 24. Rows is written, okay, as column, minus 12, 24. You have 4 times of LE square, that is 64, minus 6 LE is there, so be careful, that is minus 24. 2 LE square is there, that is 32. So your row will be your column, 32, 12 as usual, minus 6 LE minus 24, minus 24. 4 times of LE is 64. Once you have determined this, okay, our next intention is to find the, since we have only one element, one stiffness matrix, means our elemental stiffness matrix is our global stiffness matrix. Okay, now we need to find out the load vectors. Now when you want to find out the load vectors, look at the diagram carefully. Here you need to find out two load vectors. One is a load vector due to the point load. In other words, you need to find out the load matrix due to point load, and you need to find out the load matrix due to this uniformly distributed load. So that is what I'm going to teach you now. Now look at the problem carefully. I'm going to keep both the diagrams. Yeah. Now the load vector due to point load means, is there any point loads acting at node 1? So V1 will be caused by the force F1 and theta 1, and V2 is due to F2 and theta 2 is due to M2. Is there any force acting? No force is acting at node number 1. So F1 is 0. Any moments at node 1? No. F2, yes, a force is acting, but that is moving in a negative direction. So that is 100 into 10 power minus 3. Is there any moment acting at node 2? No. So this is how you are going to write. Now, in order to find out the uniformly distributed load, so you are going to use the formula. So this is the formula: F naught into L by 2, F naught L square by 12 minus F naught by F naught into L by 2 multiplied with this is plus, okay, plus F naught L square divided by 12. So this is a formula for finding out the uh, load vector due to UDL. So you need to ask me, what is this F naught? F naught is nothing but 10 kilonewton per meter is your force value. So minus 10 into 10 power 3. Length is how much? Length is 4 meter divided by 2. So as usual, minus 10 into 10 power 3 is a force. L is 4 square divided by 12. Okay, minus 10 into 10 power 3 multiplied with 4 divided by 2. Okay, so this is a plus sign. 10 into 10 power 3, L square is 4 square divided by 12. So which is equal to, if you do the simplification, you are going to get this as minus 20 into 10 power 3 minus 13.33 into 10 power 3 and minus 20 into 10 power 3, and this is plus 13.33 into 10 power 3. Okay, now you need to take the cumulative effect of this, because on this element you can see both UDL and point load is going to act. So you need to take the cumulative effect. So now again, what I'm going to do is, see, FP is a force due to point load, or force vector due to point load, or force matrix due to point load. FU is a force vector due to uniformly distributed load. Okay, so I'm going to write the values as it is: 0, 0, minus 100 into 10 power 3, and this is 0. So here minus 20 into 10 power 3 minus 13.33 into 10 power 3 and minus 20 into 10 power 3 plus 13.33 into 10 power 3. If you just try to add the values, 0, so 0 and minus 20 into 10 power 3, 0 minus 13.33, so we're going to get 13.33 into 10 power 3 minus 100 minus 20, which is minus 120 into 10 power 3. So 0 and plus 13.33 into 10 power 3, so which will be 13.33 into 10 power 3. So this is how you are going to find out the global force vector. So next our intention is to find out the global equilibrium equation, which is nothing but K into Q is equals to F. As we all know that displacements, degrees of freedom is V1 theta 1 V2 theta 2. Okay, by looking at the diagram itself, V1 theta 1 V2 theta 2 are the degrees of freedom of the problem. Now we are going to apply boundary conditions by elimination method. Okay, generally that is a elimination method. That is a method where we are going to, that is a method we are going to use. Now look, by looking at the problem, you can see that since one end is completely fixed, that is node number 1 is completely fixed, displacements at node number 1, that is V1 theta 1, is assumed as 0. So what you need to do is very simple: V1 theta 1 V2 theta 2. I'm writing the degrees of freedom. Similarly, this V1 theta 1 V2 theta 2 are the degrees of freedom. Okay, now as usual, so associated rows and columns are to be deleted. So V1 column has been deleted, V1 row has been deleted, theta 1 column has been deleted. I'm going to delete theta 1 row. So ultimately we have left with 12 minus 24 minus 24 and 64. So the common 0.4375 10 6 has been just kept as it is, V2 theta 2, and here the force vector, whatever is there, I have taken as it is. Okay, now if you solve the above equation, you are going to get V2 as minus 87.62 into 10 power minus 3 meter. Theta 2, you are going to get minus 32.38 into 10 to the power minus 3 radians. Okay, which is an angular displacement. Okay, so by this I'm going to wind up this analysis of beams in your finite element method. Okay, thank you.